So in chapter 6, we're going to be working with combinations, permutations, and binomial theorem. 6.1 is going to deal with combinations and the binomial theorem, and we're going to continue this chapter in studying data analysis and statistics. So what we're going to talk about in vocabulary is going to be what's the idea of a combination? And the combination is about how many different subsets can you make with a larger set of data. So if I had, say, 12 different items, but I wanted to see how many different ways could I put them together 3 at a time. That might be either combinations or permutations, but if it's combinations, the order doesn't matter. So for instance, if I'm dealing cards out in a game of cards, it doesn't matter what order I receive the cards in, I still have the same hand. So that would be an example of a combination. On the other hand, if I'm talking about runners running in a race, it's very different to finish first than it is to finish third. And in that case, order would matter, and that would be a permutation. So in this section, I'm going to work with combinations, but it's important you understand the difference between them. We're going to go through Pascal's triangle. So Blaise Pascal was a philosopher and mathematician. In that time period, most philosophers were also mathematicians, kind of interesting. But Pascal's triangle is a sort of an algorithmic, easy way to remember what some basic combinations are. And we use Pascal's triangle as a shortcut to apply the binomial theorem. And what the binomial theorem is about how do I take a binomial to increasingly large powers. So you've already learned special patterns for squaring a binomial and cubing a binomial. And now we're going to learn how to create a special pattern for a binomial going to any power. So it's a lot easier to use the binomial theorem than it is to say take a binomial and take 6 of the same binomials and multiply them together to find out what that binomial is to the 6th power. So it's a lot easier than doing it by hand, and that's why we're learning how to do it. The type of problem I might want to use these skills to answer is a problem like this. So during the school year, girls basketball is scheduled to play 12 home games, and I want to attend at least 3 of them, so 3 or more. How many different combinations of games can I attend? So we're going to learn how to do the calculations necessary to answer this question. It's a relatively complicated question to ask until you learn a few things. But first, let's take a look at just how do I calculate combinations. So this is what we're looking at with combinations. So it's n is the larger set of numbers. So in the case of the previous problem, there were 12 basketball games, n would have been 12. And if I wanted to just see how many different ways there were to see exactly 3, then r would be 3. The thing that's complicated in this previous problem is it's at least 3. So that means I could see 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12 games and still satisfy that. But if I wanted to find specifically how many different ways are there to see 3 games, n would be 12, r would be 3. And now we have this new thing, this exclamation point. And what the exclamation point is that's a factorial. So if I want to go ahead and find from a set of 10 objects, how many different ways are there for me to arrange 3 at a time, I'm going to take the n, that's 10, factorial, over 10 minus 3 factorial times 3 factorial. So I just identified n and r, and I plugged them into this formula. But if I don't know what a factorial is, that doesn't help me. So a factorial is the number shown times all of the integers below it, down to 1. So 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And you'll find on your calculators you have a factorial key. I don't use the factorial key much. Okay, and I'm going to show you why. So 10 minus 3 factorial, that's 7 factorial times 3 factorial. Well, 7 factorial is this. 7 times 6 times 5 times 4 times 3 times 1. So I can cancel those with that. And 3 factorial is 3 times 2 times 1. So if I cancel the 3 With the 9, I get 3. And the 2 into the 8 gives 4. So now I have 3 times 4, which is 12, times 10. That's 120. All right, so I didn't need a calculator to do this problem. Once you've done the canceling, it's normally very simple math. Okay, so let's do another one. I'm going to have 7 factorial over 7 minus 5, that's 2 factorial, times 5 factorial. Okay, and you'll notice over here 7 plus 3 is 10, 2 plus 5 is 7. So you can't add these together, but if you look at to make sure you don't make a mistake, if you look at these numbers, they would always add up to be 7. So 7 factorial is 7 times 6 times 5 factorial. And that's going to cancel with this 5 factorial. And 2 factorial is 2 times 1. 2 goes into 6 and leaves 3. Obviously, you notice I ignored the 1. Anything divided by 1 is just itself, so the 1 doesn't really come into play. 7 times 3 is just 21. Okay, so that's just practicing combinations, and it's pretty easy once you get used to identifying the right parts and plugging them into the formula. Okay, so let's take a look at this idea. They want to know how many different ways are there for me to come up with 5 face cards. Well, if I have kings, queens, or jacks in the deck of card, there are 4 kings, there are 4 queens, and there are 4 jacks. So that means n is 12, r is 5. So if I want to find the combinations of 12 items taking 5 at a time, that's going to be 12 factorial over 12 minus 5 factorial, which is 7 factorial times 5 factorial. Okay, so 12 is 12. 12 factorial is 12 times 11 times 10 times 9 times 8 times 7 factorial, which will cancel with the 7 factorial. And 5 factorial is 5 times 4 times 3 times 2 times 1. So these cancel. And I know that 5 will go into 10 and leave 2. 4 times 3 is 12, so those will cancel with that completely. 2 will get rid of that too. And so my answer would simply be 11 times 9 times 8. Well, 9 times 8 is 72, so then it'd be times 11 would be 720 plus 72. This is going to be 792. So there's 792 different ways to create a 5-card hand using just kings, queens, or jacks. Okay, now this was a single event, right? The single concept of dealing out 5 cards. When you want to start looking at multiple events, then calculating probability is a little different. So we're using the combinations to calculate probability. Probability is basically a percentage ratio, and it's the number of things you're looking for out of the total number possible. So we're not yet calculating probability, but this inherently was sort of a probability problem. Okay, but we use combinations and or permutations to identify some of the parts in a probability calculation. So when I want to talk about multiple events, finding the number of ways both event A and B can occur, I would need to multiply or add, right? So it's really about whether it's and or. When it's this happens and then that happens, those are 2 events. So the probability of the first, or the number of ways the first thing can happen, and the number of ways the second thing can happen, get multiplied together to find out the number of ways this will happen and then that will happen. Okay, so when there are 2 events, and that's the key, is it 2 events or 1 event? If there are 2 events happening, you multiply to find out the number of ways it can come out. In the case of this happening or that happening, right, then only one thing is happening. It's not that 2 separate things are happening. One event is happening, but it can come out either of a couple of ways. That's when I add. Okay, but the key thing is whether or not there are multiple events. And becomes multiplication, or, which makes one event, is addition. Okay, so if I wanted to find a deck of dealing out a set of 5 cards and having at least one spade, how many different ways are there that could come out? Well, if you think about it, there are 13 spades in a set of cards. So how many different ways are there for me to come out with at least one of them is an interesting question. So I could have one spade, or I could have 5 spades in order to justify at least one spade. I could calculate the possibilities of having 1 or 2 or 3 or 4 or 5, and I could add them together. Or I could find the probability of having none and then subtract that from all possibilities. So those are sort of the different choices that I have. So one of the things you want to take a look at is it easier to directly calculate the thing happening, or is it easier to calculate the thing not happening and taking it out of the total amount of possibilities? And in this case, for me to do at least one spade, I could find out the probability of having 1, and then 2, and then 3, and then 4, and then 5, all the way up to 13, but I'd have to do 13 separate calculations, and that just does not sound fun to me. So instead, what I'm going to do is I'm going to find the probability of having no spades at all. That's one calculation, and subtract it from all the possible ways I could have a 5-card hand with 52 cards. So what that's going to do then is going to remove all of the different situations in which there were no spades, and that will answer my question. So when you work on a problem like this, you want to think about it a little bit before you just launch into doing the work. So first I'm going to calculate the probability of having no spades. Well, if there are no spades in the deck, then the deck is much smaller. Instead of 52 cards, it would only have 39 cards. So I want to find the number of combinations taking the 35 9 spades 5 at a time. And that will be 39 factorial over 39 minus 5, which is 34 factorial, times 5 factorial. And if I write that out, that's going to be 39 times 38 times 37 times 36 times 35 times 34 factorial. And you'll notice I only write the numbers out till I get to the largest factorial I have in the denominator, because these are going to cancel. And then 5 factorial is 5 times 4 times 3 times 2 times 1. And I know that 5 goes into 35 and leaves 7. I know that 4 goes into 36 and leaves 9. I know that 3 goes into 39 and leaves 13, and 2 goes into 38 and 19. And if I multiply 13 times 19 times 37 times 9 times 7, I'm going to get 575,757. Okay, so this is the total number of hands that don't have spades in a deck of cards. But then I have to subtract that from the total number of hands I can get in a deck of cards in order to find out the number that have at least one spade. So now I'm talking about the number of combinations of taking 52 cards, the whole deck, 5 at a time. And that's going to be 52 factorial over 47 factorial times 5 factorial. So I'll have 52 times 51 times 50 times 49 times 48 times 47 factorial. So you notice these things sound like, oh, this is so much work, but I've got 5 numbers multiplied together divided by 5 numbers multiplied together. That's what I'm ending up with. And when I simplify, 5 goes into 50 10 times. 4 goes into 52 13 times. 3 goes into 48 16 times. And then 2 will go into the 16 8 times. So it's going to be 13 times 51 times 10 times 49 times 8. And what that equals is 2,598,960. And if I subtract this out then, 575, 757, I'll find my answer, which is 2,023,203. And this is the number of hands in a deck of cards that have at least one spade. So again, I could have calculated having one spade, having two, having three, having four, all the way up to 13 and added them together, and I would have gotten this same number. But it was much easier to figure out how many hands don't have spades and take that out of the total number of possible hands. So for those of you who are interested in thinking about odds and probability and gambling and cards, and you think about poker, so you think about a royal flush, there are 4 royal flushes in a deck. Your odds of getting a royal flush is 4 in 2,598,960, so really unlikely. Okay, so practice some of this work. Do problems 3, 7, 14, and 17. And then come on back and we're going to talk about Pascal's triangle. So Pascal realized that there was a pattern to the coefficients in binomials being taken to higher and higher powers, and he saw that that pattern related to combinations. Okay, and Pascal's triangle is the triangle which is all these combinations, so 0, 0 at a time, 1, 0 at a time, 1, 1 at a time, 2, 0 at a time, 2, 1 at a time, 2, 2 at a time. So all the different possibilities with 0 things, 1 thing, 2 things, 3 things, 4 things, 5 things. And it's very easy to build Pascal's triangle further and further down. So you'll notice though that this is a little non-intuitive. We don't start with the first row. The top row is 0 because it's relating to taking 0 things 0 at a time. There's only one way to do that. Okay? So 0 level, the first level, second, third, fourth, and fifth. Okay, now if I want to make the 6th row, you'll notice that these terms in the middle, the outer edges are all 1s. So I know that if I want to make the next row, the outer edges will be 1s. Because any time I take something 0 at a time, there's only one way to do it. And if I take it 5 items 5 at a time, or 6 items 6 at a time, or 4 items 4 at a time, there's only one way to do that too. So when n and r are equal to each other, the solution will be 1. And when r is 0, the answer is 1. Okay, so that's what happens every time you do these things. Now these internal numbers, you see 1 plus 1 was 2. 1 plus 2 is 3. 2 plus 1 is 3. I can find these internal numbers by simply adding the two numbers above it. So 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. And 5 plus 1 is 6. So I can keep building out Pascal's triangle however far I need to. Okay, and that's really helpful. It's very easy to just keep building new and more levels. So I have the 5th, the 6th, the 7th level, and I could keep going on forever if I wanted to. Or I could follow this pattern that you'll notice how the pattern of R is that it's 0, 1, 2, 3, 4, 5. Right? And you notice that n stayed the same for the level. Right? So I could continue to build Pascal's triangle down, or let's say that I wanted to get the 21st level of Pascal's triangle and I didn't want to take all the paper necessary to build it all the way down that far. I could simply say, oh well, I know that the 21st level of Pascal's triangle will be 21, combination of 21 to the 0 power, and then the combinations of 21 to the first power, dot, 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 on and on and on until I got to the end, would be the combinations of 21, 20 at a time, and 21, 21 at a time. Okay, so you should do whatever you feel is easiest, right? That's what you should do. All right, so let's go ahead and just sort of work with Pascal's triangle. So I want you to do problems 27 and 28. So if I want to do a binomial expansion, that's what I'm going to do here. You're going to find that when I expand a binomial, it creates a bunch of terms. And each term, I'm going to tell you, each term has 3 parts. So it has a coefficient part. It has the first term being taken to a power. That's another part. And it has the second term being taken to a power. And you may look at what the book has presented here and say, oh, wait, Mr. Rynerson, this only has 2 parts and this only has 2 parts. And that's because they've hidden some information from you. So this is 1 times a to the 4th power times b to the 0 power. And this is 1 times a to the 0 power times b to the 4th power. And they've kind of hidden that away from you. Okay, so what I want you to remember, the zeros are kind of placeholders. Remember, anything to the 0 power is 1. 1 times the rest of it just becomes the same thing. So it doesn't have any bearing on the value. But it's important to keep an eye on the places that you're at and not get confused about what power you're supposed to have in each individual term. Okay, and the zeros help you do that. So if you take a look at this, these coefficients 1, 4, 6, 4, and 1, I'm going to talk about where they come from in a second. But when we look at these terms, the a, you'll see the a starts at that term, right? This term. And then it descends, the third, the second, this is the first power, right? And then the 0 power. And if you take a look at the second term, the b, it starts at the 0 power and it ascends. Right? And if you think about other things you've already learned, so you learned a pattern for a plus b cubed, and you learned that it was 1a cubed plus 3a squared b to the 1st power plus 3a to the 1st power b squared plus 1, I left it out in the first one, a to the 0 b cubed, right? And this would have had b to the 0 power. So when you looked at this pattern, you learned this pattern, we didn't talk about these, but you did the same thing. I have a to this power descending, 3, 2, 1, 0. I have b to this to the 0 power ascending to this, so 0, 1, 2, 3. And you'll notice that in each term, if I add the exponents, 3 plus 0 is 3, 2 plus 1 is 3, 1 plus 2 is 3, 0 plus 3 is 3. They always add up to whatever is the power. And that's the same here. 4 plus 0 is 4. 3 plus 1 is 4. 2 plus 2 is 4. 1 plus 3 is 4. 0 plus 4 is 4. Those are things to help keep you on track. Because so now I know what to do with these terms. I have to know where to get these coefficients. Well, these coefficients represent the combinations possible with this number. 4 to the 0, 4 taken 0 at a time, 4 taken 1 at a time, 4 taken 2 at a time, 4 taken 3 at a time, and 4 taken 4 at a time. And they come from Pascal's triangle for the level of that power. Okay, so now I'm going to apply that. This is a pretty big one. It's going to be a little difficult. But I need to figure out what is the 8th level of Pascal's triangle. So I could do all these combinations, or I could go back to where I was and go, oh, here's the 7th level. I had already done that, but I built up, while you were working on those other problems, I built up the 8th level here. So it's 1, 8, 28, 56, 70, 56, 28, 8, and 1. And if I come back and I put those in here, so I have 1, 8, 28, 56, 70. Let me make sure I'm doing those right because I was working off memory. 1, 8, 28, 56, 70. All right. And then they're going to go back down the other side the same way. So plus 56. And I'm going to use 2 lines to do this. I want to be really clear and leave a lot of room. My handwriting's pretty bad, as you're probably already aware by now. plus 1. All right, so these are the coefficients from the 8th level of Pascal's triangle, and they're the coefficients here in my binomial expansion. So that's one of the 3 parts. Now I want to take A, and I'm going to take it to the 8th power and descend. So I'll have A to the 8th, A to the 7th, A to the 6th, A to the 5th, A to the 4th, A to the 3rd, A squared, A to the 1st power, and my placeholder A to the 0 power. Now if I've done it right, I'll have a power of A for each one of my coefficients. That's why I also want to keep that 0 power. Now I'm going to start with B squared to the 0 power and ascend. So I'll have B squared to the 0 power. I'll have B squared to the 1st. I'll have B squared squared. I'll have B squared cubed. I'll have B squared to the 4th. I'll have B squared to the 5th. I'll have B squared to the 6th. I'll have B squared to the 7th. And I'll have B squared to the 8th power. Now if I want to double check, I could look at my exponents. 8 plus 0 is 8, yeah. 7 plus 1 is 8. 6 plus 2 is 8. 5 plus 3 is 8. 4 plus 4 is 8. 3 plus 5 is 8, 2 plus 6 is 8, 1 plus 7 is 8, and 0 plus 8 is 8. So I've laid it all right. I've laid it all out right, and now what I want to do is I want to simplify it. And by simplify, I mean I'm going to take B squared to those different powers, and I'm going to get rid of redundancy. Like I don't need coefficients of 1, and I don't need powers of 0. So this becomes just A to the 8th. And then I'll have 8, A to the 7th, and B squared to the 1st power is just B squared. And then I'll have 28, A to the 6th, and B squared squared is B to the 4th. Remember, when I take a power to a power, I multiply the exponents. Then I'll have 56, A to the 5th, B to the 6th, plus 70, A to the 4th, B to the 8th, plus 56, A to the 3rd, B to the 10th, plus 28, A squared, oops, making a mess, 28, A squared, B to the 12th, plus 8, A to the 1st, B to the 14th, and I ran out of room again, plus B to the 16th. Okay, so this is a relatively complicated one to do because I had B squared. I didn't just have B like in this problem. So after I wrote it all out, then I also had to simplify. Okay, and you're likely to have that kind of thing. Right? If I want to go ahead and do this, this is to the 6th power. Okay, so I'm going to go back to Pascal's triangle and I'm going to get the 6th level. That was this level here. So 1, 6, 15, 20, 15, 6, and 1. And I'm going to go ahead and put down 1, 6, 15, 20, and then they go back down the other side with the same numbers, 6 and 1. And now this is going to be a little complicated because now I've got this coefficient 3. It's also part of this. So I'm going to have 3u to the 6th, and I'll have v squared. I may not even have enough room for this. I need a lot of room. All right. and then I'll have v squared to the 0 power. And here I'll have 3u to the 5th. I still didn't make enough room. This is complicated because by the time you get done writing all this stuff, it gets to be pretty big. Okay, so I'll have a lot of space, and then I'll take the time to simplify it. V squared to the 1st, right? And again, 5 plus 1 is 6. My exponents always add up. 3u to the 4th power, v squared to the 2nd power, 3u to the 3rd power, v squared to the 3rd power, 3u squared, v squared to the 4th, 3u to the 1st power, v squared to the 5th, and 3u to the 0 power, v squared to the 6th. And when I simplify, I'm going to have to take this 3 to the 6th power. So I'm going to whip out a calculator and do that. I don't feel like doing that. So 3 to the 6th power is 729. We'll sort of keep the calculator floating around. 729. And then u will be to the 6th power. And v squared to the 0 power is 1, so it goes away. Then I'm going to have 6 times 3 to the 5th power. Oh, I got to go back and find 3 to the 5th power. So I'll have 3 to the 5th power is that, 243. But then I have to multiply it times the 6, times 6, and I get 1458. A big number. 1458. And u will be to the 5th power. And v squared to the 1st power is v squared. Right, now I have to take 3 to the 4th power to do this one. Okay, so I'm going to do 3 to the 4th power. That's 81. But I have to multiply it times 15. Times 15. 1215. Okay, so 1215. U will be to the 4th power. And v squared squared is v to the 4th. I got to make sure my u's look like u's. Okay, now I'm moving on to this one. I'm going to take 3u to the 3rd power. Well, 3 to the 3rd power is 27, times 2 is 54, and then times 10 would be 540. So 540, u is going to be cubed, and v squared to the 3rd power is v to the 6th power. And then 3 squared is 9. 9 times 15 is 90, and 45 is 135. U squared. And I have v squared to the 4th power. That's v to the 8th. Right, and I'm going to, again, use another line here. So I'll have 3 to the 1st power. That's 3 times 6 is 18. U to the 1st power. V squared to the 5th power is v to the 10th. And then 1 times 3u to the 0 power is 1, times 1 is 1, times v to the 2nd taken to the 6th power is going to be 1v to the 12th. Okay, so this was a pretty complicated binomial. Again, I had coefficients, I had exponents in the terms in the binomial, but you just take it a step at a time, pull the 3 parts. You've got the coefficient from Pascal's triangle. You've got the first term starting at this power and descending in powers. You've got the second term starting at the 0 power and ascending in powers. And then you simplify. Yeah, it took a little time, but it's really not hard. Okay. Now, what happens when this was a minus? In each case, I had pluses in my binomials. And so you notice that all the signs were pluses. There's no way for the sign to change. But when there's a minus here, it really isn't that it's any different. It's just that my first term here is c, and my second term is -4. So if you use -4 as the second term, it will take care of everything and it will make all the signs. But there's also a way to sort of cheat the system and do it a different way. And I'll show you how to do that too. Okay, so we're going to be really literal and mathy, and we're going to go, okay, well, this second term, this is really C, this binomial is really C plus -4. So my second term is actually -4. Okay, I need the terms from Pascal triangle's fifth row, so 1, 5, 10, 10, 5, 1. I'm going to go back and I'm going to use those. Thank God these things keep getting smaller. I'm going to do pluses again. I probably didn't need quite that much room. All right, so let me move this one over. Move them back a little. I left a lot of room. These aren't as bad. Okay, so I know that I'm going to take C, and I'm going to take it to the fifth, and then the fourth, and then the third, second, first, 0. And I'm going to take -4, and I'm going to need a little room at the end there. And then I'm going to take -4, I'm going to do -4 to the 0, -4 to the first power, -4 squared, -4 cubed, -4 squared, I'm sorry, to the fourth power. So I ascended and then I started descending again. Be careful. I should have caught that when I do my next check. Okay, so I caught it right away when I said it because I went, that doesn't make any sense. But, right, 5 plus 0 is 5, 4 plus 1 is 5, 3 plus 2 is 5, 2 plus 3 is 5, 1 plus 4. See, if I'd done it wrong, I should have caught it about here. So I wouldn't have had the right number. 1 plus 4 is 5, 0 plus 5 is 5. Okay, I did it all right. And now, -4 to the 0 power is 1. 1 times 1 times c to the fifth is c to the fifth. And then -4 to the first power is -4. Times 5 is -20, so this becomes -20 c to the fourth. And then -4 squared is 16, positive 16, times 10 is 160, so that's plus 160 c cubed. And then -4 to the third power is -64, times 10 is -640 c squared. And then -4 to the fourth power, I believe, is 264 times 5. I'm probably going to have trouble with doing that right. So let's make sure we know this. We have 4 opposite, and then we want to do up caret 4 is 256. Okay, so I was right about that. Times 5, 1280. Okay, so it's plus 1280 c to the first power. I don't have to write first power. And then -4 to the fifth power. Oh, I better do that again. So I have -4 to the fifth power, -1024. Minus 1024. Remember, c is going to be the 0 power, which should just be 1. It's not going to change anything. Okay, so there it is done in the very mathy way where I said, okay, this second term is -4. But there's another way you could go about doing this. You could say, you know what? I'm going to ignore all that. I'm going to build my all my terms. I'm going to build them using just 4. And in this case, what I've been doing is I've been going one term, I put the coefficients in, then I put one term in, then I put the second term in. What I'm going to do is I'm going to build the whole thing because you might find that easier. So I know my coefficient was 1, I know that I have c to the fifth, and I know that I have 4 to the 0 power. Right? And I'm going to go to the next term, and I know I have 5, and I know I'm going to have c to the fourth, and I'm going to have 4 to the first. You notice I'm ignoring that 4 is negative. Then I'm going to do 10 c to the third, 4 squared. And then I'm going to do 10 c squared, 4 to the third, and I'm going to do 5 c to the first, 4 to the fourth, and then I'm going to do 1, c to the 0, 4 to the 5th. And what always happens when this item, when the sign in the binomial is negative, is this pattern happens. The first is negative, and then it alternates. So it goes minus, plus, minus, plus, minus, plus. And that happens because, right, the 0 power, it just becomes 1. So it doesn't change the sign out in front. But whenever I have an odd power, and I'm always going to have the first power here, it's going to make the sign here negative. And whenever it's an even power, it's going to make it positive. So it will always alternate to the end. Right? So if this is easier for you than doing it this way, by all means, go ahead and do it, and you'll get the exact same results. Okay, so that's a couple different ways to go about that. Go ahead and practice expanding binomials. Do problems 20, 24, 28, and 29. Come on back and we'll solve that problem about the basketball games. Okay, so if you'll notice, I want to attend at least 3 of the games. So much like the problem where we had with the cards and the spades, I could find out how many different ways there were for me to attend 3 games, 4 games, 5 games, 6 games, 7 games, 8 games, 9 games, 10 games, 11 games, and 12 games. I'd have to do 10 different calculations and add them together. Or I could find out how many ways there are for me to do 0 games, 1 game, and 2 games, and subtract them from the total number. Right? So what might be a little complicated is thinking about, well, how many different ways are there to make the decision about going to these games? Well, in each case, I can make 2 decisions. I can either say yes or I can say no. So the total number will be 2 to the 12th power. 12 different times of making a decision that has 2 outcomes. The different ways that could work out is 2 to the 12th. And then I'm going to subtract the combinations of going to 1 game, right? So that would be 12 games, sorry, no games, 0 at a time, right? Combinations of seeing 1 game, and the combinations of seeing 2 games. If I add these guys together, I'm sorry I put commas in, but I really wanted to put in pluses. If I find the probabilities of not attending at least 3 games, it's a lot easier, and I only have to find 3 instead of having to find 9. Okay, so there is only one way to not attend any of the games. There are 12 ways to attend a single game, and in this case, I'm going to do this calculation. I'm going to have 12 factorial over 10 factorial times 2 factorial. So that's going to be 12 times 11 over 2 times 1. 66 different ways I could do that. So I know I'm going to have, 2 to the 12th minus this value. 13 and 66 is 79. Okay, so now I'm going to go back to my calculator and figure out what is 2 to the 12th. 2 to the 12th power is 4,096 minus 79. The answer is there are 4,017 different ways for me to attend at least 3 games. Okay, so that's a beginning start into the ideas of combinations. Also working with using combinations to do binomial expansions and solving problems using combinations.